In this video, we're going to quickly generalize the results of the previous example problems to see how they can give us some general equations. Before we do that though, I just want to offer a word of encouragement. If any of you have ever been inclined to sleep through one of my lectures, you are actually in good company. This guy's trying to make me feel like I'm actually in class right now. He can't even with all this calculus, so he's checked out of life for a few hours. I don't really blame him. Bio-Silverart law can be a little tedious, but that's okay. So, in the previous two examples, we looked at the magnetic field of a long straight wire at a particular point and the magnetic field of a loop of current at the center of the loop. I'm just going to write those formulas down. Or I'm going to write down the general formula, which I've already done in the previous videos. This is just to convince you, or not to convince you, but to solidify everything. Mu naught I over 2 pi r theta hat. This is the magnetic field of a long straight wire. In the example, we had looked at it at a particular point where the point was, I think, a distance a away from the wire. This now is a general result where r is going to function as our variable, mu naught I over 2 pi r. And the theta hat is what we're going to have to deal with. So we saw again on that video that if I look at this current edge on, this is going to give me concentric circles of my magnetic field, and so the theta hat is a unit vector that points in the theta direction. What is theta but the direction moving around this wire? So if this pin is the unit vector, at every point that unit vector will be tangent to the circle. You have to be careful with these when you're integrating because they are definitely not constant. They're constant in magnitude but not in direction. But the theta hat will tell you the direction of the magnetic field. Now, of course, do I mean theta hat like this or theta hat like this? That is going to be a function of the right-hand rule for field. What is the right-hand rule for fields? Well, I've said it before. The way I formulate it is to differentiate between my thumb and my fingers. And my fingers are going to point in the direction of whatever is curved. My thumb is going to point in the direction of whatever is straight. And in this case, I've got a straight wire. So my thumb points in the direction that's straight. My fingers then wrap around in the direction of the field. And so as I've drawn it, this current is coming out of the page. My thumb comes out of the page. My fingers then tell me the direction. So the theta hat tells me that it's forming concentric circles. The direction is going to be given by the right-hand rule. Of course, I could just as easily put a current into the page. Then I put my thumb into the direction of the current, which is into the page. My fingers then wrap around and tell me the direction of the field. And as you can imagine, it's exactly reversed from this situation. All right, now the other one we did was the magnetic field at the center of a coil of wire, a coil of current-carrying wire. So I'm going to write down the general formula for that, mu naught I over 2r, where 2r, well, r is now the radius of the coil of wire. Notice the absence of the pi. That just came out of the geometry. But r is the radius of the coil. This is the center of a circular current. So how do I determine this? Well, first of all, let me draw the wire. So let me put the current flowing counterclockwise. Notice this is going to look very similar to these, but in these cases, the current is straight and the field is curved. And my current is curved, therefore my field will be straight, right? That's my rule. Put my fingers in the direction of whatever's curved, my thumb in the direction of whatever's straight. In this case, the current is curved, so I wrap my fingers around the current in the direction of flow, and I stick out my thumb. That tells me that at the center I've got a magnetic field coming out of the page. Again, if I flip to the direction here, you can probably imagine what's going to happen. I will wrap my fingers around the current this way, stick out my thumb, and that gives me at the center a magnetic field into the page. So nothing wrong with this equation as long as you remember this is only valid at the center of a loop of current. And here's our general equation for the field of a long straight wire at some distance r away from the wire.